This is group 3 and we will be presenting our model of a direct conversion digital flat panel detector. So the flat panel detector is made of a cardboard box covered in black kite paper. So the first layer is the photoconductor, which is represented by a piece of foil, and to the sides there are electrodes. So the second layer is the TFT array, which is represented by a piece of paper on which the array is drawn. The third layer is the glass substrate layer, which is represented by a piece of plastic in which there is a piece of glass inside.
I'm going to be presenting on the photoconductor layer. So as we could see here, this is the photoconductor and there's two electrodes on each side. So the photoconductor layer is made of amorphous selenium and directly converts X-ray photons into electrical charges. A high voltage top electrode creates an electric field that drives these charges down to pixel electrodes below, where they are collected and read out to form a high resolution digital image.
I am Mukhtar Agunanan and I will be explaining the second layer in our direct conversion digital flat panel detector model. So this layer is the second layer, which is the TFT array. It is represented by a piece of paper on which the array is drawn. As you can see towards the bottom here, the little square at the top represents the storage area. The square at the bottom represents the thin film transistor or TFT, and the area in between represents the sensing area. So the thin film transistors or TFTs are responsible for the readout of the electrical signal which goes to the ADC. The TFT array functions as a switch, allowing the stored charges to be read out pixel by pixel. Each pixel in the detector has its own TFT, which ensures precise control over the signal transmission. I am Harsha Raghunandan and I'll be talking about the glass substrate layer of the flat panel detector. So the substrate layer provides mechanical support, optical clarity, and thermal stability, making them ideal for high resolution and durable displays. The glass substrate is typically made from specialized glass with low thermal expansion and high strain resistance. During the manufacturing process, the glass undergoes precise scoring and breaking techniques to ensure durability and reliability. The substrate layer is represented with a piece of plastic and a glass inside of it.
Hi, my name is Sonia.
And I'm Jada.
And today we'll be presenting
the flat panel detector indirect type conversion.
We'll be showing the different layers as the X-ray passes through the detector. This is the protective layer. It is made up of cardboard and wrapped in foil. It protects against any scratches, dents, or moisture.
Okay, so this is the scintillator layer, right? It is made up of cesium iodide and it absorbs the X-rays and converts them into light, right? And it is made up of a square piece of foam, styrofoam, and wrapped in cling wrap.
So this is the photodiode array. It is made up of amorphous silicon. It absorbs the light from the scintillator layer and converts it into electrical signals or charges. The materials I used for this was wire, cling wrap, and cardboard cut in little squares.
Now,
Okay, so this here is a thin film transistor. Each photodiode is connected to a thin film transistor. This here is the storage capacitor, right? So the thin film transistor gathers and collects electrical charges, which then reads, processes, and digitizes, right? Collectively, then an X-ray image will be formed. Okay, so my thin film transistor is made up of a square piece of cardboard which is wrapped in foil. These white lines here are white strips of Bristol board, and these here are the plastic pH or binder separators. And then we took a red marker to draw in the storage capacitors.
So this is the substrate layer. It is usually made out of glass, and this provides support and serves as a base for the TFT array. Okay, so this is made up of cardboard box, but is meant to represent the glass and is wrapped in a piece of paper.
Okay, that is the thin film transistor. This is the photodiode. Then we have the scintillator layer. And last but not least, the protective layer. Thank you for listening, and we hope that this presentation was informative.
Photography by Group 3, Understanding the Key Layers of CR Imaging Plates. On this slide, we see an overview of the layers of a CR imaging plate. The protective layer, made of a thin clear polymer, it prevents scratches, wear, and static buildup that can attract dust and reduce image quality, represented by the clear bag in the image. It is designed to be thin enough to be protective without blocking or attenuating any X-ray beams, ensuring a clear image is achieved. The phosphor layer in CR imaging, represented by salt in the image. The phosphor layer is typically made out of photostimulable phosphorus, typically barium phosphate. When exposed to X-rays, it stores the latent image by trapping electrons in a metastable energy states. During processing, a laser beam stimulates phosphorus, releasing this energy as visible light. The supportive layer in the computer radiography flat panel. It is represented by the newspaper, matchstick box, and cardboard box in the image. The supportive layer provides structural stability and mechanical strength to the phosphorus layer. It ensures the plate is remaining flexible yet durable during handling and processing. This layer also maintains proper alignment of the phosphorus crystal, preventing damaging and distortion of the X-ray images. The conductive layer in CR imaging plates. This helps dissipate static electricity that could interfere with image quality by reducing statoelectric buildup. It prevents dust attraction and artifacts. Additionally, it enhances signal transmission by minimizing unwanted scatter of light during laser stimulation, improving image clarity.
The reflective layer redirects scattered photostimulated luminescence photons towards the scanner's optical collector. Without this layer, up to 50% of the signal could be lost, reducing image brightness and detail. Titanium dioxide is commonly used as the reflective layer within CR cassettes. This layer helps redirect emitted light from the phosphor towards the imaging plate and ensures that more light reaches the detector rather than being lost, enhancing the overall sensitivity of the system. The backing layer serves a protective function and contributes to the durability of the imaging plate. It shields the back of the cassette from physical damage and environmental factors. It helps maintain the integrity of the imaging plate, ensuring it remains stable during handling and exposure. It is typically made of a flexible material that absorbs impact and reduces wear. In conclusion, the various layers of computed radiography imaging plates each have distinct functions that collectively ensure high quality X ray imaging. From protection and conservation of X rays to support and reflection, understanding these layers is essential for optimizing image quality and ensuring accurate diagnostic results.